Okay. Yeah. Okay. Previously, we have learned about vectors. So today we will aim to learn a certain part of vector analysis, that is gradient. Gradient. Now, before going into the gradient topic, we will first learn what are differentials. Differentials. So, uh, we will start defining what differentials are. Differentials. Now consider an independent variable, that is x. So independent in the sense that we have a dependent variable. Let's suppose that is y, and these are connected by a function f. That is y is dependent on x via f. F is of some function. Now, if I increase x to some extent, let's say delta x, we increase x to x plus delta x, then due to this increment, y would also increase to y plus delta y, because the very reason that y is a function of x. So here we have delta y. So now y plus delta y is nothing but function of x plus delta x. So therefore delta y is f of x plus delta x minus fx. Now if we consider this, we have some idea, we have some elementary idea of what a limit is. Limit. Limit in the sense that if we do this, if I tend delta x to 0, meaning this increment goes infinitesimally small, goes infinitesimally small, then we write delta x as dx, and this is known as differential of x. Differential of x, and in this limit delta x tends to 0, we have delta y also tending to dy. that not immediately tends to 0, but a prime x dx. We define it as this. We define delta y, that is the increment, that is the infinitesimally small change of y, as a prime x dx, where a prime where a prime is nothing but this: limit delta x tends to 0, f of x plus delta x minus fx divided by delta x. So we define a prime x to be the limit delta x tends to 0, f of x plus delta x minus fx by delta x. So this is our very definition of a prime. A prime. We call it like that. That is the first order derivative of a f with respect to x. That is uh, that is first order derivative of f with respect to x, with respect to x. Now, similarly, we define a prime prime x, that is the second order derivative of f with respect to x, and also nth order derivative, that is dnf by dxn, that is the nth order derivative of f with respect to x. Now, now this is all we have when we have one independent independent variable, that is x. Now what happens when we have two independent variables, let's say x comma y? What happens then? Let's suppose we have a function of such variables x, y, and this is like z. Say, say we have z, that is a function of x and y, and we have this time two independent variables, that is x and y. Now if I increase x to x plus dx and y to y plus dy, then what happens to z? Then what happens to z? We define we define that z goes to z plus dz. Now dz is nothing but f of x plus delta x comma y plus delta y minus f of x comma y. Now I write I write it as this. We write it at this fashion, that is f of x plus delta x comma y plus delta y minus f of x comma y plus delta y plus f of x comma y plus delta y minus of f of xy. So now this can be written like this, that is f of x plus delta x minus f of x. We have y here. As this is fixed, we are not considering the fixed part here. So delta x, and then so this is one part plus f of x comma y plus delta y minus f of x y divided by delta y. Now this becomes then a prime, sorry, this becomes then f x fx. Oh, I have to change the ink. Fx x comma y dx plus fy x comma y dy. Here fx xy is the first order partial derivative of f with respect to x, that is limit delta x tends to 0 f of x plus delta x comma y minus f of, sorry, plus delta y. Oh, we can also neglect that x comma y divided by delta x. As y is fixed here, we can neglect the delta y part. We can neglect it. So this is first order derivative of f with respect to x. Now what is fy xy? That is limit delta y tends to 0 f of x comma y plus delta y minus f of x comma y divided by delta y divided by delta y. So this is it. Fx, that is the first order partial derivative of x with respect to, sorry, first order partial derivative of f with respect to x, and fy is the first order partial derivative of f with respect to y. So this means when we have two independent variable x comma y, then delta z, that in the limit delta x tends to 0 and delta y tends to 0 becomes dz is del f del x dx plus del f del y dy. So this is differential of z when this z depends on two independent variables x and y. Now comes the three-dimensional part, that is when we have three independent variables. Three independent variables, that is x comma y comma z. Now let's suppose in this case we have a dependent variable here, that is phi, and phi depends on like this x, y and z. Now, in similar fashion, d phi would be like this: del phi del x dx plus del phi del y dy plus del phi del z dz. Now we can write this as this: I cap del phi del x plus j cap del phi del y plus k cap del phi del z dot I cap dx plus j cap dy plus k cap dz. And the first vector, the first expression, we it is a vector first of all, this expression and this expression. So what we have done is that we turn a scalar into a dot product of two vectors. That is, one is called the gradient of phi dot, another is called the infinitesimal differential vector of r. This is known as gradient of phi, and this dr and this dr is infinitesimal differential of r, infinitesimal differential of r. So we have defined what a gradient is. That is, we write without phi here because of the uh, definition we are giving, that here this a vector over delta is known as gradient, that is I cap del x plus j cap del y plus k cap del z. So this is our gradient vector. So this is our gradient vector. Now we have to say something about gradient. Whenever whenever this gradient acts over phi, this gives a vector, that is sum a. Now this a depends on x, y and z. So this is a variable. It's a variable that depends on x, y and z. Now now so we have d phi equals to grad phi dot dr, grad phi dot dr. Now if I take the modulus here of gradient, grad phi dr cos theta, so where theta is the angle that grad phi makes with dr, this is the theta. Uh, and this theta is actually dependent on x, y and z on certain points. This theta is dependent. So whenever, okay, we write dr as ds. Now infinitesimally small change of position, if I take the modulus here, this becomes ds, and we write d phi as a, suppose just a vector, and cos theta as cos theta. So this becomes here d phi. The change in phi becomes some scalar times the infinitesimally small displacement into cos theta. So whenever so d phi gets maximized whenever theta becomes 0, that is cos theta becomes 1. Then d phi becomes d phi max, d phi maximum, that is ads. So so phi so d phi becomes maximum when a vector is parallel to dr vector, that is whenever grad phi uh, changes along the curve we 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 uh, we draw we go along the curve we go whenever delta phi grad phi changes along the curve we go, that is along that is along dr, then then d phi gets maximized, so grad phi denotes the direction along which d phi is maximized, along which d phi is maximized. Now another point here, for a certain surface, let's suppose phi equals to constant, we have d phi, that is change in phi would be 0. That implies grad phi dot dr becomes 0. This means grad phi is perpendicular to dr. This means if I go along the surface, if I go along the surface dr, this grad phi would be perpendicular to the surface grad phi. Then here grad phi denotes normal to the surface phi x y z equals to c. So we will stop here.